Hi, my name is Chen. I'm a physicist, and today I work as a data scientist at IronSource. And I'm very happy to guide this panel. We have two guests today. The first one, Professor Ron Folmaמ. He's the head of the atom chip group at Ben Gurion University and the Nanofabrication Center. He's doing many amazing things. I encourage you all to go to YouTube and see his movies, especially the one about a single atom clock in 2 places. Very interesting and very recommended. He's doing a lot of interesting things in his lab, and hopefully we'll hear some of it today. And the next guest doesn't need much introduction. Shohat is a unique kind of virtual capitalist. He's the founder and a partner at Alpha VC, and also has a very strong technical background. He told me today that he still writes code. And he has a very great contribution to the Israeli high-tech community in Israel at all. Why don't we start with each of you tell us just a few minutes. Ron can tell us a few words about the work you're doing in your lab. I think it's on. Okay. Just a few words about the projects you have in your lab.
Okay, good evening, everybody. The idea behind the atom chip is actually to try and imitate 2 revolutions very well known that came from miniaturization. One we all know is about 40, 50 years ago, the miniaturization of the transistor or electronics into integrated devices. This enabled everything we have today, really, our phones, the computers. So this was one revolution. The second revolution was the miniaturization of optics, what we now call photonics, maybe 20, 30 years ago. This enabled a lot of the communications that we have today. So what we're doing with the atom chip is really trying to take quantum technology, which today exists in very large labs. If you go into a lab, say of the atomic clocks that today give the time standard in the world, it's a huge lab. Lasers, electronics, vacuum chambers. You find a lot of infrastructure around, and the idea is to put all that on a small chip to make it more robust, cheaper, but it's more than that. It's also much more accurate in terms of how we integrate the different parts of the technology together. And so the performance is supposed to be eventually much better as we go to the small dimensions of a chip with these large labs. So it's many orders of magnitude in miniaturization. We find a lot of interesting physics questions that need to be solved. Just to give you one example, if you go to that lab of atomic clocks that I told you about before, you find that the nearest material object to the atom, which does the timekeeping, the nearest material object is very far away, maybe centimeters away. In a chip, the nearest material object will be microns away. And so there's a lot of interaction there between the atom and this chip. And we have to do a lot of physics in order to understand how we can suppress all the hindering effects of this closeness. So that's pretty much what we're doing.
So what we do is simple, right? We invest money, hopefully in order to create good returns for our LPs. So venture capital I'm the simpleton in this panel. So venture capital is knowing very little about a lot. Aleph manages now 350 million. We generally, the way for people here to understand kind of what drives us as VC, and this will be helpful in this discussion of what can be invested in. We manage now 350 million. If you look at our fund 1, it's 150 million. For us to be good at what we do, we need to return about 450 million. So about 3x, because it's over a long duration. Generally, VCs are 7 years, extended to 10. Aleph is 12 years, extended to 15. So in that period of time, you actually need to return at least 3x on capital. You would usually own between 15 and 20% of a company at point of exit, which means that you need to be part of economic value generation of about $2 to $2.5 billion, right? So that's why, for example, we announced our first exit from Fund 1 last week, a company called Luminate. It's a great outcome for the founders. It's also a very good outcome for us. It's $6 million that turned into $57 million in about $200 million exit. But if you look at the numbers, what it means is that 200 million economic value is a tenth of what we need at the minimum in order to create the returns. So most interesting for venture capital, and that's part of the reason why we're interested in the area of quantum, is step functions, right? So step functions create opportunities that allow us to funnel money into in order to help people pursue a dream that hopefully is a generator of the kind of value that VCs need for an exit. Background, as you mentioned, is technical, but it's not really interesting.
Okay, thank you both for coming. This is a kind of open discussion, so please feel free to ask questions. But I will start with a general question. If you look at quantum technology, starting from the basic idea of okay. Okay, if we look at the quantum technology, starting from the basic idea of quantum computer that Feynman presented, today this technology evolved and we looked at quantum communication, quantum sensing, and a lot of different domains. What is the industry that you think will have the best impact or the most change due to quantum technology? Where we will have the most impact?
Well, first of all, the map that was shown previously, it's a very nice map, but it still lacks a lot of paradigms or a lot of topics that should be added. One of them, for example, is quantum materials. It's somehow related to the topic that was mentioned, which is topological matter. Another one is simulators. So I think that before we have really serious quantum computers, we'll have simulators. Now, simulators could have a lot of applications. Actually, Feynman originally talked about simulators. And one example would be medical applications. I think the ability to simulate chemistry and to design new kind of drugs would be enhanced tremendously. So there are many applications out there. Let me just give you a few of them. And then maybe later on, if you want, I'll give some examples of companies that deal with them around the world. Some of them were not mentioned previously. So let's talk, for example, about sensing, okay? Systems are becoming extremely sensitive with quantum technology. And so if once before the age of GPS, we would navigate on inertial navigation systems, these were mechanical gyroscopes that were turning around. So today we have acceleration sensors that are based on something called atom interferometry that are supposed to be, at least theoretically, 10 orders of magnitude better in acceleration sensing. So that's a big jump. I don't know how much of these 10 orders we'll be able to realize eventually, but even if we make the jump 5 orders of magnitude, that would be amazing, especially in an age where people are very cautious of GPS. There's GPS jamming, which is very easy. Now there's GPS spoofing, which is becoming more easy. People are talking about GPS firewalls, but people really want to be independent of GPS. That's not only for military purposes, but all the many civilian infrastructures are now dependent on accurate time and position.
It's basically a standalone system that doesn't need satellites.
Sure.
Right, for showing location.
So you'll have your it's an inertial navigation system. It's a standalone system. You'll have a box. Rumors have it that the US Army is already using them. For example, in submarine navigation, they don't come out of the water for a very long time. So they're very sensitive to acceleration. Of course, clocks, accurate clocks are also very much needed for good navigation because time is also distance. You would need also very good sensing of the gravitational field of Earth to find, again, military application would be, I don't know, bunkers, tunnels, etc. But civilian applications would be to find minerals, water, and so on. So these are devices, again, atoms, that are extremely sensitive to the gravitational field of Earth. So much so that there are, again, rumors that US submarines are now navigating the topography of the Earth, of the surface of the ocean. So for example, now they do it, you know, the usual thing is to do it with sonar, but they want to be completely quiet. So when they go close to, I don't know, the Russian shores or something, they turn on these gravitational sensors and they give them a map of the mountains and the valleys as if they had eyes outside the submarine, so they could really navigate by sight. These sensors of gravitation field are becoming so accurate that there are even papers out there saying that as jets become more and more stealth to electromagnetic radiation, which is today the radar is electromagnetic radiation, the only way to really see them is by quantum radars, which would see their gravitational signature. So imagine how small that is, the gravitational signature of a plane. It sounds really mind-boggling, but the background actually is quite small if you look up into the sky. So these kind of sensing machines are really mind-boggling in their abilities, and there are quite a few companies out there that are already dealing with them.
To whomever seen the Big Bang Theory series, the device that are bidding for the US Army is exactly what Ron talked about now, a GPS, which is a so it's a standalone system. Okay, my next question is to Eden. As a VC, what are the tools you have to examine a new startup in a technology which is so novel and so new, and you don't have a lot of reference for other companies, probably not enough experts in the field? How can you examine how to invest in startup in the quantum technology fields?
Well, the lack of experts is actually part of the problem, right? So you actually want to invest in people that have a clue, and generally there's a pretty short supply of that in general. So it's not about the due diligence, it's actually about the company building in the area of talent. So the real answer is it's pretty hard to predict the future, right? So the problem is that sensors is an interesting example, right? So sensors, if you look historically as an investment vehicle, it's not a great investment vehicle, right? It's mind-boggling what you can do with that, but generally the way it works is the technology has a maximum of value to its customer base, and then over time it gets copied, and there's a race to the bottom, and components generally become fairly cheap. And what's important is relationship with the customer. So as venture capital, what you look for is choke points. It sounds bad, right? But choke points allow you to extract value from the value chain. So if you look back, and history doesn't repeat, but it rhymes. So you look at the x86 infrastructure system and the ecosystem, and how Intel was able to take control over that ecosystem by owning the instruction set. And initially by trying to own IP and owning some of the layers, but at the end of the day, it was the x86 instruction set, which makes QM, for example, quantum machines, so interesting, because if you can own control, and if you can own the instruction set through owning the control, then that's a real choke point that allows you to do value extraction from an ecosystem. So as a VC in general, especially in a new ecosystem as that, you're trying to find reference points that says, okay, let's assume the world of compute will be taken over by quantum. So let's assume 10% of compute will go towards that. In such an ecosystem, in such a predicted ecosystem, where are the points where owning certain assets can make a difference? So one example is obviously the instruction set. The other example that you'd expect to be a choke point is, for example, bus formats. And you actually see the bus has been a very bad area for you to invest in. So if you look back on the x86 system, because bus is an interoperational infrastructure, then you actually need to publish it, then you actually need to have a committee own it, like PCI bus. So you can't actually use PCI as a way for you to extract money from from the value chain. So in general, what we're looking for is either on instruction set is in the areas where you collaborate, where between different systems, where it's absolutely fine for one of the sides to be homogeneous. That's generally where opportunity lies. It seems abstract, but if you analyze through many markets, generally that's the area where the bigger companies are born.
Maybe I can add something. You asked me before to try and predict what would have the most impact. I didn't really answer your question. So of course, that was hard to predict.
Okay. Yeah. Yes, please continue, Ron.
Okay, so it's really hard to predict. We can maybe predict timelines of when we will get to certain points in technology. It's very hard to predict how the market will react in terms of, what it will be used for and how many people will use it. But let me just say a few words. First of all, quantum computing, in its real sense of many qubits and doing something really practical, I think is very far away. On the other hand, things like very good clocks, as small as a chip that could go into your iPhone, are quite close. Magnetic sensors are quite close. So there's a huge, broad band of timescales with which we can define, maybe also for the map that you're building. Timescales are very important because they're very broad in quantum technology. Let me give two examples of perhaps surprises. One is a company called ID Quantique, a very nice Swiss company that does quantum communication. And they told me that they were very surprised they started to build actually building blocks for quantum communication. For quantum communication, you need to be very good in all kinds of building blocks. Yeah. So one building block, very simple building block that they now sell, it's like a USB device, is what they call a true random number generator. All the usual random number generators in a PC are not really true, they repeat themselves after some sequence. A real true random number generator is if you take a photon and it impinges on a piece of glass, you never know, no theory on Earth can predict if it reflects or transmits through that glass. On the basis of that, you can make a true random number generator. Such a simple idea. Anyway, they just built it. They didn't want to sell it. They just built it as a sort of building block for their eventual system of quantum communication. But they were very surprised that it was selling, according to them. I didn't check the numbers, but it was selling hot donuts. And to where? Who was the customer? The gaming industry. The gaming industry suddenly wanted to have the stamp of quantum technology inside. They were very surprised, so they started selling it to the gaming industry. I fell in love with their product. I bought it. It's on my table, $1,000, although I have nothing to do with it right now, but it's still standing on my table. They have like 2 dices on their,
You can fill the lottery based on it.
Yeah, and another example of maybe a surprise is that everybody thinks that the magnetic sensors are going to be used, for, I don't know, military applications, defend some facility against, I don't know, something. But actually, there may be surprises there because now the prices of drugs, of the clinical tests for drugs, especially brain drugs, is really becoming inhibiting. And so if somebody can come up with a process that FDA or somebody would feel that they're reliable in examining what a drug really does, that could really cut costs and time. And so if you have very good quantum magnetic sensors, atomic magnetic sensors, which you place very close to living neurons, a living tissue of neurons, and we're very close to that point, and now put in your drug, you'll see exactly how the activity changes without any interference. This is passive measurement by just checking the magnetic fields that the neurons, as they fire, they emit magnetic fields, of course. So it's so sensitive, so it's completely passive. Nothing touches actually the neurons. And so it looks like it's a very reliable system, and that could really be good for the market. So this could be a surprise. So there are all kinds of twists in the game that could make the products go for a big market. Yeah.
This is why we need to stop talking about quantum computing and more about quantum technologies.
Yes, exactly.
Yeah. Okay. So,
by the way, just to add, sorry, somebody came to me from the music industry and said, look, I have to put an atomic clock into my systems. And I said to him, what do you need an atomic clock? You don't need such a time accuracy. He said, I want to synchronize my, my music when I transmit abroad and so on. I said, you really don't need it. He said, yes, but it's such a hype that I don't care if it adds something to the technology. I just want to be able to write quantum technology inside. So even that is becoming...
this is marketing, quantum marketing. Do you have any questions from the audience? Oh, should I continue? Okay. If we look at what happens in the world, we know that the Chinese government now invested $11 billion in a quantum research center. Europe invested just now $2.5 billion. Huge companies, Google, IBM, and so on, invested a lot of money in this area. What are the chances, or how can Israel compete with it in order to stay relevant when this revolution is coming, in order for us to stay in the edge of technology?
I'll start off with the academia. So I'll speak for the benefit of my partner here. I think there are two angles where there's Israel has surprisingly a lot of money, but it's misused in many ways. And again, correlation is similar to AI. I think that you have three basic issues. First, bringing back labs, professionals in labs, and being able to actually finance that. I'm sitting on the board of Ramot, the commercialization entity of Tel Aviv, and I see like the misuse of being able with $10 million, $20 million, $30 million to actually make a huge difference on academia, which is not done in any proper way. So that's on the academia side. I think that we have a lot of experts. You see that also in QM and in one of the founders. So you actually see people that should be coming back. So that's one angle, which is interesting. The other one is OCS, the Office of the Chief Scientist or whatever. Anyone from the OCS here? Just making sure before I. So like. I think that the OCS has actually been a very positive force on the ecosystem in some of the years where it operated. I think that the incubator system is basically just theft from the public, and maybe that's not a popular belief, but having an incubator that does new media in the center of Tel Aviv, there's no market inefficiency in new media, right? So material science, quantum areas that actually where you have market inefficiency, where the vehicle called venture, which is actually has a good timeline, is actually quite patient, is not patient enough to make those investments. That's where the OCS should be financing health, like medical, quantum. So that's the OCS in my mind needs to basically move the amazing amounts of money it has. Just as an FYI, when the year ends, there are a lot of surpluses because generally the Ministry of Economy is holding many of the budgets and is not releasing the budgets, right? So when you get to year end, you have about $10 billion usually of surplus in the offices, and the Ministry of Economy has only two targets that can spend this amount of money in this short of amount of time. It's the military, and it's the OCS. So it's actually at the end of the year, it's driving a lot of budgets to it that are being misused in my mind. And the third would be collaboration within the industry. I think there's the like early starts of that, but you see people at Tel Aviv that don't know what the people at UG are doing and people at Weizmann. I think the academia has a lot of driver. And obviously the map is a huge initiative by itself. Where is he missing? Is he hiding there? Anyway, so these are kind of the 3 points that I'd push on.
I would say we need chutzpah. So, and that's a word actually used by the head of DARPA when he visited Israel. I asked him, what are you doing here? You have, orders of magnitude, more scientists, more money, more area, and so on. He said he's looking for Israel chutzpah. And I think that this is really what we need, because somehow the labs that I see abroad are moving very slowly from these large labs where everything is really state of the art, just a Fabry cavity in order to a local laser is $200,000 and it's really the best that the world technology can make. And I like the word FAP. FAP is for all practical purposes, F-A-P-P. You know, for all practical purposes, we just need to be good enough. We don't need to be the state of the art. We, you know, if the state of the art is 10 to the minus 19 in clocks, we need to do clocks that are 10 to the minus 15, 16, but, you know, are 3 orders of magnitude cheaper. And so we just need the chutzpah. You know, I spent a few years in the Air Force when the drones started flying. And you won't believe how much chutzpah we used to have. I mean, we used things that, you know, you would say, no, it cannot be that it's flying. For example, the motors were taken from, you know, those tree cutters. You know, so the motors for those drones were taken. And the wheels, we took wheels from baby carts, you know, just ridiculous stuff that we did. That's real chutzpah. And we got the things to fly very quickly. Whereas when you looked at similar projects for drones in the US, they were bogged down for years and years with much, much larger budgets. So we really need chutzpah.
Space-IL is a great example of that.
Yeah,
exactly. That's exactly the case.
They cancel like the competition, but they still keep going.
Totally. It's worse than you think.
Let's talk a bit about the quantum computer. Many of the tests and experiments that are done in university are done in very low temperatures and in ultra high vacuum chambers. Do you think when we get to a quantum computer that this limitation will stay, or is this a phase on the way? Or why do we need to do it in ultra high vacuum or very cold temperature?
Okay, so anything quantum needs isolation, really good isolation. I always tell the story of the Tibetan monk when people ask me about quantum technology. And the Tibetan monk goes, it's a very short story. So people, you know, in the West, they, like mathematicians and so on, they tried to solve some logic problem. They couldn't do it. They tried 20 years. They were very frustrated. And so somebody said, let's try another philosophy, another kind of thinking. They said, let's go to the East. We heard that there's some monk in some Tibetan, you know, monastery. They went there and the monk said, and he looked at the problem, said, yes, I think I can solve it. He said, great, solve it, and then send us the, you know, back the answer. He said, no, that doesn't work, because when I solve it, I have to go into a state of, you know, enlightenment, deep meditation. And once I touch a telephone or a computer or an email, that would be gone, and I would not know the answer anymore. So quantum technology is really about quantum states, and quantum states are very delicate. And the minute they touch the real world outside, which we in physics call the classical world, they're gone. And so they will need isolation. They will always need isolation. And when they don't have isolation, there's an effect which we call decoherence. Coherence is the effect of being quantum, and decoherence is the effect of going out of being quantum. And so there is decoherence, which is a very bad effect for us. But this isolation, through things like the atom chip that I was talking about before, are becoming better and better for less and less money and smaller dimensions. Let me just give you an example. If today a vacuum chamber, you go into a lab, you see a vacuum chamber built from some metallic thing and windows, laser, and it's inside, it's, you know, conditions like space. Today, we can achieve the same conditions within a chip that from the outside looks like your Intel Pentium chip. So you hold it from the outside. You think it's a normal semiconductor device, but you don't know that inside you have complete isolation. So the atoms inside, they don't touch anything. They're in complete vacuum. And these chips are already existing. And so I think that the issue of isolation would not be a big issue. In terms of cooling, there's the Nobel Prize of 1997. They got the Nobel for showing how you can cool without a refrigerator. So you don't need this liquid nitrogen anymore or liquid helium machines and so on. Josephson junctions
with lasers.
Josephson junctions still needed. But all the other things that a lot of other systems for quantum computing, like ions that were mentioned here or atoms, they can already do the cooling with laser light. So you put a tiny laser diode in a millisecond. That atom is close to absolute zero. Yeah. So the cooling today, the isolation and the cooling are becoming small, cheap, and robust. So I don't think that would be our problem. Yeah.
Even though this noise is going to cool his system in also using other stuff except of he's going to add a refrigerator because he wants to decrease to increase the vacuum. Want to go to let's say 10 to the minus 12 he preferred to put also the system, including he's going to cool the system further.
Yes, so in labs still cold is good, even for the systems, the vacuum chamber, I understand.
The question is about
in the future, I don't think that would be needed. By the way, if you speak about vacuum, that's a very interesting point. The smaller your vacuum volume, yeah, the easier it is to take everything out, yeah, take all the background gas. So people still working with quite large vacuum chambers, it's of course hard. They need, but I think that as we'll miniaturize everything, that will actually be easier.
I guess the answer is why it doesn't matter. Like at the end of the day, I think it's a question of how you deliver service, right? And because it's highly likely at this point that it will be less of machines being sold and more of cloud service, then like, yeah, well, we should find the most efficient economic way to deliver the service, but it really doesn't matter. Like if you're able to get either type of algorithms that don't require a lot of error correction or just fully error corrected, then you know that it doesn't matter. Just have the algorithms run and wherever that they need to run.
Okay. So I have somewhat philosophic questions. I think one of the key differences between classic computer and a quantum computer is when we think about classic technology, we kind of manipulate nature in order to do calculation. We use a transistor, we use a current and circuits, and if there is a current, we say it's 1, if it's not, we say it's 0. And in quantum technologies, we use the nature in its raw position. More, you use molecules and atoms in pretty much their state at nature. Well, you cool them to death almost, but basically we use them in their natural state. So do you think this is the last barrier, the last leap in technology after we will be able to do computing with molecules and atoms? Is this the last leap?
Yeah, I guess it's a bit of a nonsense, right? So you don't, right? So we will use molecule, we will use atoms, but if you look at the type of work like chemical simulations that are talked about, you're actually, the algorithm becomes the abstraction. So it's not the electrons, it's not the fact that you use semiconductors to simulate a machine or to build a machine in order to run certain calculations. At the end of the day, even chemistry simulations, you do have an abstract form that simulates a chemical system, which happens to run on a quantum circuit, but it's anyway abstracted. So I would claim it's not, obviously computationally and speed, etc. It's much faster and it has significant advantages, but I don't think it's closer to nature in that sense. Like, so just
in the sense of the hardware part, we have it.
But even then, you're abusing the hardware in order to create a system that you want to emulate.
So I think you said the words "the final leap." That scares me a little bit. I don't really know what it means. I was just invited to what they call an unconference in Oxford. And I looked at the title of the conference. It was, what will remain of our physical principles after the next physics revolution? No. It's not, these are real physicists, you know, and I was wondering whether I should go or not, because I have, you know, what can you say? You can entertain everybody. It's like you're on drugs and you go around and everybody's laughing and smiling, but there's not really much we can say about the final leap. But I decided eventually to go there because I love saying, you know, I'm going to throw out energy conservation. I'm going to throw out momentum conservation, throw out all these things enough. It's, you know, it's boring. But really, if we're trying to think of what we'll see within our lifetime, I think it's very hard to predict, especially about the quantum computer. Quantum mechanics, as far as I am concerned, is not fully understood. The quantum computer will require, at least a serious quantum computer, I'm not talking about a few qubits, but a serious quantum computer will require extreme knowledge of quantum mechanics to a level, to an engineering level, which I don't think we have. By the way, it could be that this serious quantum computer, or attempts at this serious quantum computer, will actually discover new physics, because it would be such a sensitive sensor of new physics. So just for that, I would invest a lot in the quantum computer. Yeah, not because of the technology, but as a sensor for new physics. But in terms of technology, it's very hard to know if within our lifetime we will really have a serious quantum computer. So I would, you know, putting money on it, I think it's an interesting investment, but it's a really high risk, high gain. So I would emphasize the high risk. The high gain is also there, but you know. Okay, so
what would constitute a serious quantum computer, in your opinion?
Well, everybody's talking about quantum speed up. So you would have to really, and there's several guys out there trying to prove it for D-Wave computers. They still haven't been able to do it as far as I know. You would have to really show that it's better than anything a regular supercomputer can do. And even those tests are pretty hard tests, you know, in terms of interpretation. But that's the goal, to do such a test, to prove it, to have a consensus on it. And I think we're very far away from that.
Yeah, no smart thing to say.
Ron, you said at the beginning, you can tell us a bit about companies that are dealing with quantum technologies. Maybe you can elaborate.
Yeah, sure. So there are really beautiful companies out there. A lot of my friends are opening companies around the world, and I visit them. They work very hard. I'm a bit too lazy for such an endeavor, so I really just consult, but not more than that. Let me give you a few examples. In the Silicon Valley, there's a company called AOSense. That came out of Stanford. Huge funding from US agencies like DARPA, US Air Force, and so on, for navigation systems, mainly, for gravitational sensors that I mentioned before. They're also selling a little bit on the open market, if you go to their website, but only a little bit of what they're really doing. They're being allowed to sell. But there are many other companies out there that are open to the market. For example, there's a nice French company called MuQuans. And they are making, again, gravitational sensors, atomic clocks, inertial navigation, and very nice company. Actually, one of my students is working there, and I'm very excited with what they're doing. There is ID Quantique that I mentioned before in Switzerland. There is a company for navigation called IXBlue. I think originally it's a French company, but now they opened a daughter company which is called IXAtom, where they really focus on navigation by quantum technology. Yeah, there's now a new company coming out of NIST, also some very nice people. One of them is Zach Newman. They're trying to miniaturize a new generation of clocks. So I don't know how much you know about clocks, but the old kind of clock that runs the GPS is called a microwave clock. It's on a gigahertz frequency standard. But now the clocks that are really making it to high accuracy are called optical clocks. It's a transition of 10 to the 15 hertz rather than 10 to the 9 hertz as the usual clocks. So these are called optical transition clocks. And these are very big. As I told you, the labs are very, very big. And they're joining the effort. Zach Newman and his friends out of NIST, the National Institute of Standards in Boulder, Colorado, they're joining the effort of trying to miniaturize this large room where these optical frequency clocks exist today onto small chips. I was just in Photonics West, San Francisco a few weeks ago, where he presented some pictures of their new chip. And it's actually really beautiful.
So we are approaching the theoretical barrier, basically, if you look at Planck's.
Well, I don't know about theoretical barriers. I've not seen really anything about theoretical barriers. Let me just tell you that maybe there are theoretical barriers, but they're all the time running away from us. And you know, there was a great theoretician at CERN. His name was John Bell. He actually wrote a book called Speakable and Unspeakable in Quantum Mechanics. I recommend it to everybody. And he said that there are a lot of no-go theorems. Theory is very important in quantum mechanics, obviously, and theory has developed a lot of no-go theorems, which means where we cannot go. That's, if somebody really wants to know the limit of the technology in terms of theory, he should learn these no-go theorems. There are books and books on them, a lot of heavy mathematics. But John Bell, after all this mathematics, and he was a brilliant theoretician, he came and he was asked, what can you say about these no-go theorems? He said, all I can say is that the only thing we've proven is our lack of imagination. Yeah, and that's after 50 years, you know, of studying the equations and so on. So it's very, very hard. I think the theoretical limitations are moving all the time. The theoretical boundaries are moving all the time. And I've just heard a talk about counterfactual quantum communication. And that means that, you know, until now we're working on quantum communication where in fibers or through telescopes, like the Chinese satellite that went up now for quantum communication, they send some kind of particle, you know, with information. It could be a photon, it could be something else, doesn't matter, but some kind of particle. But now theoreticians are telling us that quantum non-locality, which actually it's a very interesting thing, quantum non-locality, and it brought about papers already 20 years ago that you can do measurements without interaction. So if you look, there is a beautiful paper called Interaction-Free Measurement, where you can really sense the existence of things without a single photon hitting them, which is the smallest quanta we have in our detectors. Yeah. So this is coming from quantum non-locality, and now people are starting to design, at least in the heads of theoreticians, quantum communication systems where no particle will actually have to be transmitted through the, you know, communication channel. So you just remind me of all these crazy things because you asked me for a limit. But the limits are there, but I don't really believe them.
Douglas Adams said, I love deadlines. I love the whooshing sound they do as they fly by. So same with theories, I guess. How many entrepreneurs here? Entrepreneurs, the ones that build companies. So it's a small amount. Like how many hardware side versus software? Like how many people deal here with hardware? Software? So I think if you look at the next 5 years in the area of quantum, at least in quantum computing, probably software design and algorithms will be the larger opportunities. It will simply be like a huge margin type of outsourcing. So instead of the 50% margin that Amdocs has, it would be like 99.9% margin. So, and it's much simpler and it's much more viable and it's much quicker if you want to make money and actually build a practice. So just.
Okay, yes.
There are a lot of people who are scared of quantum technology, and you talked a lot about military applications. And in terms of cybersecurity or cryptography, they're always saying that the first one to own the technology could bring the world to its knees. So first, is the threat real? Do you feel it? Is there like a lobby against quantum technology? And second, do you believe that the entire field of quantum technology should be like a giant open source project or anything like that?
A quick answer before I pass on. So every new technology, you have that. For AI, a year and a half ago, I was invited to Oxford to Center for Existential Threat, which apparently there is one. And it's actually fairly well budgeted. And it was 2 days of top AI people, basically scenario planning, including people from the DoD, where they had their base tactic is distributed lethality, apparently, right? So there was actually someone speaking about distributed lethality and how AI will influence that, et cetera, et cetera. And by the end of the first day, I just randomly asked 5 people if you could have a big red button that delays general purpose AI by 100 years, would you press it? And 5 of 5 pressed it. Right. So if you scare people enough through that, you always find a doomsday scenario. That's it. That's in my mind. But you always, like, when you balance the kind of pros and cons, then almost always technology advancements will provide more value than danger. So, but that's just at 20,000 feet.
the other hand, doomsday only have to come once.
Sure. Yeah. There are many doomsday predicted today.
So actually, Oxford has another center. It's called the Center for the Future of Humanity.
Yeah, it's the same.
I-
It's the same one.
Okay, so they have a nice article in Scientific American, I don't know, maybe 5-10 years ago, which says that there is already, they somehow compute the probability that we're already living in a simulation. So this happening here is just some nice simulation. So,
Someday about academia.
yeah. So the question was about
The danger.
yeah, the dangers. Well, I have to tell you a little story. Sometimes when I give talks abroad, and I hear it also from my friends, there's some guys sitting in the back row. We don't know them. They're not from some university. And we show our state of the art, the latest discoveries on the board and so on. They're like smiling this little smile saying that they knew that already 10 years ago. We don't know who these guys are, but NSA, whatever. But it could already be that these guys have technology that is bringing the world to its knees, as you called it, but we just don't know about it. We don't know that we're at our knees, you know. I don't know, but you know, it's very hard to stop the technology, but I'm very much, of course, for trying to understand all the ethical issues and whether or not we need to put some boundaries or control regulations on it. I do believe in understanding what the technology can do and the dangers of it. That goes for nanotechnology, you know, what we breathe, even what's in the air, that goes to AI, that goes to many of the things we develop. Let me perhaps say that in Israel, although we're a little bit behind in quantum technology, you asked me before, and I answered with the chutzpah word. I don't want us to go away thinking that we're not doing anything in quantum technology, and I'm very proud to say that the industry in Israel already has several working prototypes that maybe you don't know about, but for example, we delivered a year ago the first cold atom prototype to a company in Jerusalem called Qubit. So it's not now working in Jerusalem. We delivered to Tasya Avirit the first working prototype of atomic magnetic sensor. And actually, some people are trying to take it into the direction of replacing, making a cheap replacement for CT and MRI scans of the brain. So things are being done. I just visited a few weeks ago quantum department in Rafael, doing beautiful work, especially on sensing, yeah, but beautiful work. By the way, when we say sensing, many different systems. When you say quantum computing, it's many different realizations. So some of them were mentioned, but there are many of them. So it could be superconducting qubits, but it could be, you know, ions, cold atoms, NV centers in diamond. There are many of them. And so if you really want to do something in any kind of paradigm here, you have to really decide what specific system, physical system you want to focus on, because they're very different from one another. But anyway, in Israel, things are picking up. So I'm hopeful. We started late. We started small, but I think that Israel is going to become a nice hub of quantum technology.
It's one of the purpose of this community and these meetups. Any more questions from the audience?
You said something about GPS spoofing and quantum computing.
GPS spoofing, yes.
Can you please tell some words more?
Well, you said also quantum computing. It has nothing to do with quantum computing. GPS spoofing, the idea is just to, you think your GPS is working, you think your navigation system is working, but actually it's not working, and you are, you know, whatever your adversary wants, you're a few kilometers off target or whatever. So it's just taking control of the signal that comes from the satellites. You have an antenna on the side, and your antenna thinks that it's the real GPS signal, but you're giving, or bad timing, whatever, and your system thinks it's way off.
And how quantum computing helps to solve this problem?
Yes, again, it's nothing to do with quantum computing. It's just inertial navigation system. Inertial navigation system simply means that you have acceleration sensors, both linear acceleration in 3 dimensions and rotation sensing in 3 dimensions. And when you integrate over these accelerations that go into some computer, not quantum computer, just a classical computer, integrating over the signals from these acceleration sensors, you know exactly where you are.
Okay, and another question. If quantum computing can help ecology and to save the life on the planet.
Wow. You want to try and answer that? Well, I have to start by saying that I was a Greenpeace activist. So you really touched, I almost got killed, by the way, as a Greenpeace activist, because one day we got the mission from Greenpeace International to hijack the Haifa Chemikalim ship that twice a week dumps toxic waste 10 kilometers from the shore. So I found myself, you know, on a Zodiac, running past the ship, jumping into the water, climbing the ship. A guy with a knife came to me. It was a real interesting story. Anyway, the environment is very important for me. Connection between, I've never thought about it actually, between quantum technology and the environment, maybe through simulation. The simulating power is going to be so strong that currently the simulations, if you look at simulations of global warming, for example, they are, you know, with a number of years ahead, they really diverge in a way that politicians say, hey, we don't believe anything you say. And, you know, scientists are not being able to be convincing enough because there are simulations, it's very hard. But you'll have such a strong computing power and simulating power that maybe this, in this sense, will be able to have more robust results about how this ecosystem called Earth planet will evolve in future years. And so in that sense, maybe that will do something good for the environment, you know.
Generally, humans destroy Earth
much
sometimes
faster.
with computers, sometimes without.
So if you save life, you're destroying Earth. So.
Yeah.
Okay, any more questions? Yes.
Just as a reference to the last point, I think that one of the more interesting people in that ecosystem is Asparo Gazjuk, I hope I pronounce his name correctly, who moved to Canada recently. And he's working on quantum chemistry and quantum computing. And the quantum chemistry side, he has a lot of interest in the way that plants are doing photosynthesis and to really figure out that kind of the chain that goes on there.
You now touched on an amazing topic that is not in the map, should be added to the map, and that is quantum bio. Now there, I was just in a conference recently in Jerusalem on quantum bio, international conference where a lot of people, very serious people came, and we're trying to learn from what nature did. For example, in photosynthesis, some people already say that it's also in the eye of birds because they can see the magnetic field of Earth, and there perhaps other examples where nature in ambient conditions, so this is room temperature, body temperature, and no isolation, that the important isolation that I talked about before, somehow nature manages to have long coherence times, so long quantum isolation without vacuum, ambient conditions again. We don't know how they do it, and the whole field of quantum bioquantum is trying to learn how nature does it, some kind of molecules maybe that protect the molecules that we wanted to stay in a quantum state. So this is an amazing field of learning for us. Yeah, and it could be that it also will have eventually a strong effect on quantum computing. Yeah.
Okay, yeah.
I read in some interview that the professor that leads the quantum computer development in Google, Martinez, he said that he predicts that they will get to quantum supremacy in like 2 years or something like that. So according to what you say, it's more like 50 years.
Well, I'm always known to be a pessimist, but let's have...
Yeah, you saw a couple of days ago, IBM was trying to recreate Moore's law through a new parameter, which is not qubits, as the quantum volume, in order to show how it doubles every year, and in their estimate in 10 years. So it's like, it's bullshit in, bullshit out. and whatever messaging is good for OKRs in the case of Google will probably matter as well. I think it goes back to algorithms. Like if you can get rid of error correction and through that reduce the number of qubits, you'll actually move much, much faster towards a working model. And if you don't, then less so. But prophecy is for fools. Okay.
Okay. Okay, yes.
We're talking about theoretical things that will happen in a year, 2 or 5. Nobody really can understand. But let's say I'm a bank, or I'm an insurance company, or I'm a Qubit-IL or something. Do I have to worry about it, or do I have even to plan in the year 2 or 3, something like this, to use this technology? Or I say, okay, we'll be ready, and then I'll have maybe better measurement for the heart or for the health, for my, or any other thing, or my computer will work faster. But as a company, do I have to do now anything to plan anything?
That's a really interesting question. I think that some companies, especially like HMOs in your last example, anything that is non-competitive will generally just move slower, and they don't need to deal with that much anyways. If you look at super competitive or resource constrained type of companies, so if you look at gas production, like British Petroleum, they care a lot about quantum computing, they care a lot about HPC, high performance computing in general, because there's scarce resources and they need to extract resources and through that have a competitive stance. So like if you ask about banks in Israel, obviously non-competitive, so and not very resource constrained, so less of a focus, maybe other than maybe cryptography, but I think it's further out than what, like now it's better understood that it's further out than what people think. So I think that in defense, that's very resource, a lot of resources available, but the impact of losing a battle is so high that they would be incentivized to do something with it. And highly competitive industries like, for example, algo trading will probably take notice and invest in that sooner rather than later. So I would use that framework to say, well, most of Israel will not give a shit because they're not in a competitive situation.
It's a really interesting question. It depends what your goal is. Obviously, you know, when they made the laser, they said maybe we can peel potatoes with it. They had no idea. So I would say that any company that has any interest in being up to date, both in terms of you know, being attractive to the customer, even banks in terms of quantum communication. I think quantum communication will come into banks quite soon. I don't know to give a number of years, but quite soon, because privacy is going to be a huge issue in future years. And I think that quantum communication is in a very good place to contribute to privacy. So I think we don't know, we're far from knowing all the applications that will come with quantum communication. So companies in general should keep really a close eye on what's happening there. Even if they don't want to sell quantum products, but what in terms of what applications can do to their business. By the way, a lot of the technology we will not have at our disposal. So people should know that, for example, US technology like AOSense that I was talking about before, it will take decades before it's allowed to leave the borders of the United States. So a lot of the technology, especially the cutting edge of quantum technology, will not be on the market. So if anybody needs it, for example, I don't know, not only military applications, but as I said, again, civilian infrastructure. There is a report, by the way, that came out in the United States that says that 13 out of 16, if I remember the numbers correctly, critical infrastructure for the existence of the United States, civilian infrastructure, is extremely vulnerable to hacking, and they really need quantum protocols, for example, GPS, in GPS denied environments, as we call them, They need quantum machines and quantum protocols to be much more robust and independent. So bottom line is, I think we'll be surprised by all the applications that come out. I think all kinds of companies out there should just have a watchful eye on what's happening there. And yeah, that's it.
Okay, this is all the time we have, sorry. Thank you again for coming here for this meetup.